1,000,000 years. That's how long it would take the world's fastest supercomputer to solve a problem that a quantum computer just solved in minutes, using less electricity than a coffee shop. That result is real, it's peer-reviewed, and it's sitting in the journal Science right now. And yet, right now, in this exact moment, tech companies are pouring more money into AI data centers than at any point in history. So either the smartest people in tech missed the biggest story of the decade, or the headlines got it wrong. Let's find out which. To understand what actually happened, you have to picture two machines standing on opposite ends of the computing world. On one side is Frontier, housed at Oak Ridge National Laboratory in Tennessee. Frontier is an exascale supercomputer, one of the most powerful classical machines ever built. It occupies a space roughly the size of 2 tennis courts, draws enough electricity to power a small town, and can perform more than a quintillion calculations every second. For years, Frontier and machines like it have been the gold standard for simulating the physical world, from nuclear reactions to climate models to the behavior of exotic materials. On the other side is a very different kind of machine. It doesn't look like a data center. It looks more like a chandelier wrapped in gold-plated cooling equipment, suspended inside a cylinder, chilled to a temperature colder than deep space. This is a quantum annular built by a company called D-Wave, and in early 2025, it did something that made physicists sit up and take notice. D-Wave's researchers, working with a prototype of their Advantage 2 processor and roughly 1,200 superconducting qubits, set out to simulate something called non-equilibrium magnetic spin dynamics. In plain language, they were modeling how the tiny magnetic properties of atoms behave and interact over time inside different crystal structures, arrangements known as square, cubic, diamond, and biclique lattices. This isn't an abstract party trick. Understanding how magnetic materials behave at this level matters for designing better sensors, more efficient batteries, novel superconductors, and next-generation memory devices. The quantum processor ran these simulations and produced results that lined up with what quantum theory predicts. That part alone isn't unusual. What was unusual is what happened when researchers tried to reproduce those same results using the best classical simulation method available, a technique called matrix product states running on Frontier. For small versions of the problem, Frontier could keep up. But as the size and complexity of the simulated system grew, the computational cost for the classical method exploded exponentially. According to the published paper, matching the quantum processor's results on the largest problem sizes would have required roughly 1,000,000 years of continuous computation on Frontier, along with an amount of electricity that would exceed the world's entire annual consumption. Let that sink in for a second. Not a faster answer. Not a slightly more efficient one. A problem that would take a machine costing hundreds of millions of dollars longer than the age of modern humans to solve, solved instead in a matter of minutes, on a machine drawing roughly the same power as a dozen homes. This wasn't published in some fringe outlet chasing clicks. It came out in Science, one of the most rigorously peer-reviewed scientific journals in existence, under the title Beyond Classical Computation in Quantum Simulation. The paper's authors called it a demonstration of quantum computational supremacy on a problem with genuine scientific value, not a synthetic benchmark, designed purely to make quantum computers look good. D-Wave's chief executive described it as an industry first, distinguishing it from earlier quantum supremacy, claims that involved little more than generating random numbers, results that were scientifically interesting but practically useless. Outside experts largely agreed the underlying science was sound. Physicists working in quantum simulation praised the work as a genuine demonstration of a quantum system solving a real physics problem beyond the reach of the best classical techniques available at the time. For a field that has spent decades promising breakthroughs that never quite arrived, this felt like a rare, concrete milestone. So naturally, the internet did what the internet does. And within weeks, the story mutated. What began as a peer-reviewed physics result about simulating magnetic spin dynamics became, in dozens of newsletters, blog posts, and video essays, a much bigger and much shakier claim. Quantum computing, the headlines announced, had just made AI data centers obsolete. Some pointed to projections that AI-driven data centers could consume as much as 17% of all electricity in the United States by 2030, and asked why anyone would keep building that infrastructure when a machine running on a fraction of the power could apparently do the job faster. It's a dramatic story. It's a shareable story. There's just one problem. It isn't quite true, and the parts of it that are true are far more interesting and far more complicated than the version circulating in your feed. Before we get to the pushback, it's worth understanding why this particular claim landed with so much force. D-Wave wasn't the first company to claim some version of quantum supremacy. Late in 2024, Google made headlines of its own when it announced that its Willow quantum chip had completed a benchmark calculation in under 5 minutes that would take one of the world's fastest supercomputers an almost incomprehensible 10 septillion years. That number is so large it barely means anything to a human brain. that was precisely the problem. Critics pointed out that Google's benchmark, while a genuine technical achievement, was essentially a synthetic test, a problem engineered specifically to be hard for classical computers and easy for quantum ones, with no real-world application attached to it. It proved quantum hardware could outperform classical hardware on a very particular, very artificial task. It didn't prove quantum computers could do anything useful. D-Wave's result landed differently because it wasn't synthetic. Magnetic spin dynamics is a real physics problem with real applications in material science, and the company explicitly framed its science paper as the first clear demonstration of quantum supremacy on a problem with practical scientific value, not just a party trick designed to win a benchmark contest. That distinction is a big part of why this particular story spread so widely and felt so much more threatening to people watching the AI infrastructure build out. It wasn't just quantum computers being fast. It was quantum computers apparently being fast at something that actually mattered. Let's start with the first crack in the narrative, because even the original scientific claim didn't survive unchallenged for long. Within weeks of the science paper's publication, researchers at the École Polytechnique Fédérale de Lausanne in Switzerland pushed back. Using ordinary graphics processing units, the same kind of hardware that powers video games and, notably, AI training itself, they managed to reproduce results that D-Wave's own estimates suggested should have taken Frontier more than a century and a half. They did it in a matter of days, using just 4 GPUs. Then came a second, more sustained challenge from researchers at the Flatiron Institute, who developed a new classical algorithm called BPTNS, short for Belief Propagation Tensor Network States. This algorithm made real, substantive progress on the exact class of problems D-Wave had used to claim supremacy, chipping away at the idea that these simulations were fundamentally beyond classical reach. D-Wave pushed back in turn, arguing through its chief development officer that the Flatiron team's approach, while a meaningful contribution to classical simulation methods, still fell short of replicating the full scope of the original science paper. It didn't reproduce the same observables, the same lattice geometries, the same problem sizes, or the same coupling structures, D-Wave argued. And it didn't touch the largest and most demanding cases in the original study. As of the middle of 2026, this argument is still very much alive. It hasn't been resolved with a tidy headline either way. What you have instead is something scientists call a moving target, a genuine ongoing contest between quantum hardware and classical algorithms, each side pushing the other to improve. That is, honestly, exactly how healthy science is supposed to work. It is also the opposite of a settled, world-changing verdict that some quantum machine has definitively and permanently outrun every classical computer on Earth. The headline writers skipped that part because, let's be honest, an ongoing academic dispute over tensor network algorithms doesn't generate nearly as many clicks as the phrase "quantum just killed something." But let's set the scientific dispute aside for a moment and ask a more basic question. The one that actually matters if you're trying to figure out whether your assumptions about AI infrastructure need to change. Even if you take D-Wave's claim entirely at face value, even if you assume their result stands exactly as published with no caveats whatsoever, does it actually mean anything for AI data centers? And the answer, according to nearly every expert who has looked closely at this, is no, not in the way the viral headlines suggest. Here's why. The problem D-Wave solved was a very specific, very narrow physics simulation, modeling the quantum mechanical behavior of magnetic spins in a crystal lattice over time. That is a fundamentally different kind of computational task than what happens inside an AI data center. When you ask a large language model a question, or when a company trains a new AI model on billions of documents, the underlying math isn't simulating quantum magnetic dynamics. It's overwhelmingly matrix multiplication, enormous grids of numbers being multiplied and added together over and over at massive scale. That's precisely the kind of workload that graphics processing units, GPUs, were built for, and it happens to be almost exactly the kind of workload that quantum annealers like D-Waves are not built for. Think of it this way. A quantum annealer is exceptionally good at a narrow category of problems, finding low-energy states in complex physical systems, optimization problems with specific mathematical structures, and simulations of quantum phenomena. An AI data center full of GPUs is built for something completely different: brute force, parallel, repetitive numerical computation across massive data sets. One expert, an IEE member who teaches technology strategy at International Business University, put it simply. Think of quantum computers and classical AI hardware as two completely different types of vehicles built for two completely different jobs, like a pickup truck and a small sports car sitting side by side in the same garage. Both are excellent at what they do. Neither one makes the other one cheaper, faster, or unnecessary. The scale of the mismatch becomes even clearer when you look at the raw numbers. A single rack of NVIDIA's most widely deployed AI training chips draws somewhere between 120 and 140 kilowatts of power, and the next generation of hardware, is projected to push well past 200 kilowatts per rack. A modern AI data center campus can contain thousands of these racks, consuming as much electricity as a mid-sized city. D-Wave's quantum processor, by contrast, ran its headline-making simulation using roughly 12 kilowatts, an impressively small number for the specific physics problem it was solving. But 12 kilowatts of quantum annealing hardware cannot train a large language model, cannot run inference for millions of simultaneous chatbot conversations, and cannot power the recommendation engines, image generators, or coding assistants that make up the overwhelming majority of real-world AI workloads today. The two numbers aren't actually comparable because the two machines aren't doing comparable jobs. It's worth pausing here to appreciate just how much money and infrastructure we're actually talking about when we say AI data centers. This isn't a handful of server rooms tucked behind office buildings. It's one of the largest, fastest capital spending sprees in the history of the technology industry, with companies committing hundreds of billions of dollars to new campuses, new power plants, and new cooling infrastructure specifically to keep pace with AI demand. Projections suggest AI-driven data centers could consume as much as 17% of all electricity in the United States by the year 2030, an almost unthinkable share for a single category of computing to claim. That's the backdrop against which this quantum story exploded. People saw a headline promising a solution that used a tiny fraction of the power for a tiny fraction of the time, and it was natural to wonder whether the entire spending spree was about to look foolish. But wondering whether something might be foolish and confirming that it actually is are two very different things, and the confirmation part is exactly where the viral version of this story falls apart. This is the part that gets lost when a niche physics achievement gets flattened into a headline about killing an entire industry. AI training and inference run on classical hardware because that is the hardware built to do exactly that kind of math, at exactly that kind of scale, with exactly the kind of software ecosystem, from chip architecture to programming frameworks to years of accumulated engineering expertise, that the entire AI industry has been built around for over a decade. Quantum computers, meanwhile, remain extraordinarily good at a small number of specialized tasks, and for now, essentially unable to touch the kind of workload that defines modern artificial intelligence. So if quantum computing isn't about to replace AI data centers, what is it actually going to do? Because it would be just as misleading to swing to the opposite extreme and claim quantum computing is irrelevant to the future of AI infrastructure. The truth sits in a much more interesting middle ground, and it's worth walking through carefully because this is where the real story lives. The first thing worth understanding is that experts who study this space closely don't expect quantum computers to replace classical AI infrastructure. They expect quantum hardware to become a complementary layer sitting alongside it. Industry analysts have described a future in which data centers begin to include what's being called quantum pods, specialized sections built to house quantum processing hardware with its own dedicated power delivery and its own thermal management systems, since quantum chips need to be cooled to temperatures colder than outer space to function at all. Rather than replacing the sprawling halls of GPU racks that define today's AI facilities, these quantum pods would sit beside them, handling a narrow slice of specialized workloads that classical machines struggle with, while the GPUs continue doing what they do best. The overall shape of energy demand inside these facilities may shift over time, but the scale of that demand, driven primarily by the ongoing AI boom, isn't expected to shrink because of quantum hardware, certainly not anytime soon. That timeline matters a lot here, because a huge amount of the confusion floating around online comes from collapsing very different timeframes into one dramatic headline. Ask people building this infrastructure right now when they expect quantum computing to reach the kind of scale where it's doing meaningful commercial work, and you get a consistent answer. Not yet, and not for a few more years at minimum. One expert, speaking about the trajectory of the field, said that for the first time they felt confident enough to say that by the year 2029, quantum machines would begin reliably performing calculations that classical computers simply cannot do, calculations with real commercial value attached to them. Notice the year, not now, not next year. Several years out, and even that is framed as an emerging capability, not a wholesale replacement of existing infrastructure. Executives working directly at the intersection of enterprise technology and quantum computing echo that same caution. One global technology leader focused on next-generation computing put it plainly: nobody serious believes the industry has reached the point of large-scale quantum deployment inside data centers. Only a small number of specialized quantum computers currently exist inside real-world data center environments at all, and the companies building quantum hardware are still working through basic industry standards just to make broader adoption technically feasible. This is not a technology quietly ready to scale up overnight. It's a technology still being fitted for the infrastructure that would eventually house it. And when quantum computing does start delivering real commercial value, the early adopters aren't going to be generative AI companies training the next chatbot. According to people working closely with enterprise clients on quantum strategy, the two industries currently driving genuine, serious demand for quantum computing are scientific research and financial services, scientific computing applications, simulating molecules for drug discovery, modeling new materials, studying complex physical systems, mapped naturally onto the kinds of problems quantum hardware is actually good at solving, the same category of problem D-Wave tackled in its science paper. Financial services firms, meanwhile, are exploring quantum computing for things like portfolio optimization and risk modeling, problems that involve searching through enormous numbers of possible combinations to find an optimal answer, again playing directly to quantum computing's actual strengths. Most other industries, including the companies building today's largest AI models, are still in a watching and waiting posture, not a building and deploying one. There is, however, one place where quantum computing intersects with AI infrastructure in a way that is genuinely urgent right now, today, not in 2029, and it has almost nothing to do with speeding up computation. It has to do with security. And this, more than any headline about killing data centers, is the quantum story that companies running AI infrastructure actually need to be paying close attention to. Here's the issue. Modern encryption, the kind protecting everything from your bank details to a company's proprietary AI training data to the weights of the models themselves, relies on mathematical problems that are extraordinarily difficult for classical computers to solve, things like factoring enormous prime numbers. A sufficiently powerful, fully error-corrected quantum computer, the kind that doesn't exist yet but that serious researchers expect to eventually arrive, would be able to solve those same problems in a fraction of the time, effectively breaking the encryption schemes the entire digital world currently relies on. That future quantum computer doesn't exist yet, but that hasn't stopped a very real threat from forming in the present. It's a strategy security researchers call harvest now, decrypt later. The idea is simple and, frankly, unsettling. Sophisticated attackers, often nation-state actors with long time horizons, don't need a working quantum computer today to start stealing your data today. They can intercept and quietly store massive volumes of encrypted information right now, betting that a sufficiently powerful quantum computer will eventually exist to crack it open. For a piece of sensitive data with a short shelf life, that's not much of a threat. But for something like a proprietary AI model's training data, its architecture details, or years of accumulated inference logs, information that retains its value for a very long time, that ticking clock is a real and rapidly growing risk. If your defenses look solid today but rely on encryption standards that quantum computers will eventually break, you may already be leaving the vault door open without realizing it. This is why, across the technology industry, the migration toward what's called post-quantum cryptography, encryption methods specifically designed to resist attacks from future quantum computers, has stopped being a theoretical best practice and started becoming an operational deadline. Regulatory bodies in multiple countries are already pushing organizations that handle sensitive data toward these new standards. For companies building and operating AI infrastructure, protecting valuable training data, proprietary model architectures, and sensitive inference logs, this migration isn't optional homework to get around to eventually. It's arguably the single most concrete, immediate, and consequential place where quantum computing and AI infrastructure genuinely collide right now. And it's a story that generates far less viral engagement than the phrase quantum just killed something, even though it deserves significantly more attention from anyone actually responsible for protecting valuable digital assets. So let's pull all of this together and answer the question we started with. Did quantum computing just kill AI data centers? No, not even close, and not for a very long list of concrete, well-documented reasons. The underlying scientific result is real. D-Wave's demonstration, published in one of the most respected peer-reviewed journals in the world, does appear to show a quantum processor outperforming the best available classical simulation methods on a specific, narrow, scientifically meaningful physics problem involving magnetic spin dynamics inside crystal lattices. That is a genuine milestone for the field of quantum simulation, and it deserves recognition on its own terms. But that result was also almost immediately challenged by other researchers using ordinary GPUs and a newly developed classical algorithm. And the scientific argument over exactly how much classical ground has been reclaimed is still actively unfolding as of today. More importantly, even if you accept every part of D-Wave's claim exactly as published, it doesn't translate into anything close to a threat against AI data centers, because the two technologies aren't competing for the same job. AI training and inference run on classical GPU hardware because that hardware and the massive software and infrastructure ecosystem built around it over the last decade is specifically built for large-scale matrix computation. Quantum annealers are built for a narrow category of physics and optimization problems that look nothing like training a language model or running inference for millions of users. A quantum computer solving a magnetic simulation problem in minutes tells you essentially nothing about whether it could ever train or even meaningfully assist in training a large AI model, because those are, at a fundamental level, different kinds of computational problems entirely. What's actually happening, according to the people building this infrastructure and the analysts tracking it closely, looks nothing like replacement and much more like gradual, careful coexistence. Quantum hardware may eventually take up residence inside dedicated pods within larger data center campuses, handling narrow specialized workloads in scientific research or financial modeling, while thousands of GPUs continue doing the heavy lifting of AI training and inference right next door. The overall shape of computing infrastructure will likely shift and diversify over time as quantum hardware slowly matures, but the scale of demand for AI compute, driven by an industry projected to consume an ever-growing share of the world's electricity in the years ahead, isn't going anywhere. If anything, the two technologies appear headed toward becoming neighbors inside the same buildings rather than rivals fighting over the same infrastructure. And the part of this story that deserves your genuine immediate attention isn't a dramatic headline about extinction. It's a quieter, less flashy threat that's already unfolding in the background right now. The slow-motion race to migrate sensitive data and encryption standards before quantum computers, powerful enough to break today's cryptography, actually arrive. That's not a headline built for clicks. It's a genuine operational deadline facing every organization that stores valuable data today and expects that data to still matter in 10 or 20 years. So the next time you see a headline claiming some single quantum breakthrough just made an entire trillion-dollar industry obsolete overnight, it's worth pausing before you believe it. Ask what the underlying result actually measured, ask who challenged it and how convincingly, and ask whether the technology in question is actually built to compete with what it's supposedly replacing, or whether it's solving an entirely different problem dressed up as the same headline for the sake of a few more clicks. In this case, the real story wasn't that quantum computing killed AI data centers. It's that a genuinely impressive scientific achievement got flattened, exaggerated, and repackaged into something far more sensational than the truth, while the quieter, more urgent story sitting right underneath it, the race to secure the world's data, before quantum computers can crack it open, barely made a headline at all. That's the story worth paying attention to. Not the death of an industry that isn't dying, but the quiet, ticking clock running underneath it that very few people are talking about, and that almost everyone building the future of technology needs to start taking seriously today. Quantum computing is still going to change the world. It just isn't going to change it the way this particular headline promised. The real trajectory looks slower, stranger, and far more collaborative than any single dramatic breakthrough could capture. A gradual layering of specialized quantum hardware alongside the classical machines that will keep training and running AI systems for the foreseeable future. Somewhere down the road, those quantum pods really might sit beside the GPU racks, quietly solving the narrow category of problems they were built for, while the rest of the data center hums along exactly as it does today. That's a less thrilling headline. It also happens to be the truth, and the truth is usually the story worth telling.